Welcome back. Today's topic is magnetic boundary conditions. In the last lecture, we have discussed about the different types of magnetic materials. We have seen the diamagnetic materials, paramagnetic materials, ferromagnetic materials, antiferromagnetic materials, and ferrimagnetic materials. And we have also seen the concept of magnetization, and we have also discussed about the BH curve and how it is used in electrical engineering. Now, moving ahead, today we'll discuss about the boundary conditions, which are very similar to that which we have seen in the polarization and dielectric materials. So I hope that by the end of this video lecture, you will be able to develop boundary conditions between magnetic materials and utilize them for computing magnetic fields. Even though this is a broader one and it is outside of your syllabus, I hope that at least you will be able to remember the boundary conditions so that you can employ them for determining the magnetic fields. Now, coming to the introduction part, as we have already seen that the boundary conditions do help us when we are calculating the fields. Let us suppose there is a boundary, or we call it as an interface. Let us suppose this is one medium and this is another medium. If we know the fields in this one, we take B and H. Right? So this is the field intensity and this is the flux density. If we know these in this medium, then we can calculate the same in this medium with the help of the boundary conditions. We have tried with electrical quantities in unit number 1 and 2. Now we can apply the same for this magnetic fields also. But there are few conditions which are to be satisfied to apply the same old equations. Now, as you can see in this figure, that this is considered to be a magnetic interface. Now this is one medium and this is another medium. Okay, so now on this interface, now I'm considering a small region. Okay, this is my small region. Now this medium is having mu1 and this region is having a relative permeability of mu2. Now I'm considering this particular region. And now, first of all, let's take a Gaussian surface. Now, as it has already been shown that I'm considering a closed path which is on the boundary between the media 1 and 2. Now, if I apply Gauss law for the magnetic field, you know that for the magnetic field, the surface integral of the flux density vector is equal to the flux which is enclosed by that area. So if I take this media 1 and this is media 2, if I consider any region, so the B will be in this direction, right? It can be in any direction. So whatever the flux which is coming, whatever the flux density which I am counting in this particular area, that will be equal to the amount of flux. So how much flux will be there? That is nothing but my flux density in that area. So the same Gauss law is applicable for magnetic fields also. Now I am considering this particular area, right? So half of that area is in my medium 1 and the remaining half of the area is in medium number 2, right? So now what I will do is nothing but I'll take very minimal distance. So I will feel that it is having only two surfaces. This is one surface, this is another surface. This surface is 0. Okay. So now the flux is either coming out in this way or in this way, right? So this I'll consider it as Bn1 and Bn2. Okay. So now, which means that this is the flux which is normal to this surface, isn't it? So if I consider this pillbox now, if I do apply this equation, because So whatever the flux which is coming out of this one. So normally what happens is Bn1 and Bn2 will be in the same direction, but since I'm considering in opposite directions, what now I'll be getting this equation. Surface integral of b dot ds is equal to 0. So what is surface integral of b dot ds? It is having four surfaces, but I'm considering only two surfaces. This is one and this is the other one. So the first one is b1 dot n1 dot delta s. So which means that this one is delta s, and I'm considering this vector. So b1 dot n1 into delta s. Similarly, b2 dot n2 into delta s. The summation is equal to 0. So this can be taken, if I consider delta s as common and send it to other side. This is my expression. So both n1 and n2 both are same, right? So but they are in opposite direction, right? So that's why if I take them and if I remove them, what I'll be getting is bn1 is equal to bn2. I can directly write it. bn1 is equal to bn2. That is b1 cos alpha 1 is equal to b2 cos alpha 2. Similarly, I can take the same medium. Now I'll take a region like this. Instead of pillbox, I'll take a region like this. Okay. Now, if I apply the Ampere's law for this region, you know that line integral of h dot dl is equal to 1, isn't it? So, if I apply the same here, now this is, I'm going to consider these lengths, L1 and also L2. So, tangential ht1 delta L minus ht2 delta L is equal to I. Isn't it? Because both the vectors in opposite directions, right? So that's why I have taken as minus. So if I consider current also in terms of my length, I'll get it as k into delta L. So if I substitute it here, if you take delta L as common, so what I'll be getting, ht1 minus ht2 is equal to k, where k is nothing but my current density. Okay. Now, if this one is equal to 0, do remember, if this one is equal to 0, then what I'll get, ht1 is equal to ht2, which is very similar to my equation, et1 is equal to et2 for electrostatic fields. Right, this can be written as h1 sine alpha 1 is equal to h2 sine alpha 2. Do remember, this is valid only when my current density k is 0. Okay. Now if I join these two conditions, you know that if I join these two conditions, my final equation will come mu1 by mu2 is equal to tan alpha 1 by tan alpha 2, which is very similar to that of my, isn't it? Which is similar to that of my electrostatic fields. The only difference between electrostatic fields and magnetostatic fields is that in this condition, both equations do look similar, but for that to happen, we should consider k is equal to 0. Current density k must be equal to 0. Okay. So we'll solve similar problems just like the electrostatic fields in the tutorial class. Okay. So that's it for today. We'll discuss more in the class. Okay. Thank you. Yeah. Don't forget to solve this problem which we have already done in the class. Okay. Thank you.